Hello everyone, welcome to the video lecture series of Cryptography and Network Security. I am your instructor Dr. Umesh Prajapati, and today I am going to discuss the advanced encryption standard algorithm. So let's see the agenda of this video lecture. The first, advanced encryption standard. Second, AES structure. So let's discuss the first point, advanced encryption standard. Now, the RISDEL proposal for AES defined a cipher in which the block length and the key length can be independently specified to be 128 bit, 192 or 256 bits. It means the RISDEL has proposed one stronger algorithm, and it is called the advanced encryption standard. Now here the different types of blocks lengths are there. The first 128 bit block length, 192 and or 256 bit block length. But now generally we are using the 128 bit key, 128 bit block length. Now in the previous session we have seen the DES algorithm, data encryption standard. So why we need AES, advanced encryption standard? Now in the DES we are use the 56 bit key, 56 bit key, and in the AES we are use the 128 bit key length. The first difference. And second difference, it is a vulnerable. DES is a vulnerable for brute force attack. It means if the cryptanalyst try to find the characteristics of the DES algorithm, AES is a stronger algorithm compared to a DES, because here we are using the 128 bit key length, and in a DES we use the 56 bit key length. Now second, it is a faster compared to a DES algorithm, and second, and AES is a more secure compared to a DES algorithm. So why it is more stronger compared to a DES algorithm, right? We will see in the next slide to why it is more secure compared to a DES algorithm. Now let's see the different types of block size and the different type of bits, and different type of block size and the different type of key length. So here, if the key size is defined in words, bytes and the bits. It means words. It means that the one bit equal to one word equal to 32 bits. It means the group of 32 bit is equal to one word. Or if we define the bytes, the 16 bytes and 128 bits. Same for key size is a 6 words, 24 bytes, 192 bits, and the key size is 8 words, 32 bytes, and 256 bits. So these are the size of the key, and the size of the key is defined in the words, bytes and the bits. That means I already discussed a group of 32 bits is equal to one word. Now if the 16 byte equal to 4 words, it means in a one column it considered as a 4 byte. The next column is again considered a 4 byte. So total the 4 cross 4 matrix are there. Here in an AES algorithm it representing in the matrix form. So the matrix form is 4 cross 4. So total is a 16 bytes. Now let's consider the block size. Again the block size is considering the words, bytes and the bits. So the 4 words, the size of the block is 4 words, size of the block is 16 bytes, and the size of the block is 128. Now the next is the size of the block is 4 words, size of the block is 16 bytes, and the size of the block is 128 bits. Same, the 4 words for block size, 16 bytes for block size, and the 128 bits for block size. Now the next is number of round key size is again defined in words, bytes, and the bits. The same 4 word, 16 bytes, and the 128 bits. Same, the 4 in the next column, the 4 words, 16 bytes, and the 128 bits. Same for last column, 4 words, 16 bytes, and the 128 bits. Now, number of round. In a DES, we have seen the total number of rounds is 16. Now, here the key size is 128 bit. The number of round required 10. If the number of bits is 192, you have required the number of round is 12. And the key size is a 256 bit. Then you have required the number of round is 16. Now generally in all the scenario, in all the scenario, 128 bit is used in a 128 bit use, and the number of round is required 10. Now let's see the general scenario of advanced encryption standard. So now here you can see this is the AES algorithm. Now we can input the 128 bit plain text. Now it means we can input two things in the AES algorithm. The first, plain text, its size is a 128 bit. Second, key, its size is a 128 bits. Now we apply now. Both the input goes into the AES algorithm. After applying the AES algorithm, it's generating a 128 bit ciphertext. It's generating a 128 bit ciphertext. So this is the simple scenario of advanced encryption standard. Now, next scenario, I already discussed. There are two inputs goes into AES algorithm: 128 bit plain text and a 128 bit key size. Now this is the simple structure. Now in a AES there are total 10 number of rounds. It means if we have considered the key size is a 128 bit key, then we have required the 10 number of rounds. Before going to see the process of round, the first is add a round key. In add a round key, we input two things. The first 128 bit plain text, second 128 bit key, and it represents the K0. Now in add round key, we are perform XOR operation. It means we are performing a XOR operation on a 128 bit plain text along with the key K0. Now AES key expansion, during the AES key expansion we are generating a number of words. It means in the each and every key we are generating the words, and the size of the word is 4 byte. It means in the K0 the size of the word is W0 to 3. In the next, the size of the key is again the 4 byte, and it represents the word 4 to 8. The number of words is input. Number of words are input to the AES algorithm. Now after applying the XOR operation in an add round key, it's generating some output, and the output of the add round key will be given input to the round 1. And in the round 1 also we are input the key K1, and during the K1 key we are generating a sub words, and here its input is W4 to 8. Now its size is a 4 byte, or we can say that its size is a 16 byte, and the size of the word is a 4 byte. It means in a K1 key we input the 4 byte word, and the size is K0, K3 to K4 to K8. Now in the round 1, the round 1 consists of the number of transformation operation. The first, in round 1, the first transformation is a sub byte. Second transformation operation is a mix column. Third transformation operation is shift rows, and the last is add a round key. So these are the 4 types of transformation operation are considered in each and every round. Only the difference is the round number 10, only 3 transformation operations are used. The first sub key generation, then second is a shift rows, and third is a add a round key. These 3 transformation operations are used in the last round 10. Last round. Now again the output of the round 1 will be given input to the round 2, and we are using now we input the second key K2 in the round 2. Now again we are performing a various transformation operation in round 2 up to so at round n. Now in the last round, I already discussed in the last round the cyclic difference. The difference is only the transformation operation. In the round 1 to 9 we are using a 4 transformation operation. In the round 3 we are using the 3 transformation operation. So this is a simple difference in round 1 to 9 and the last round 10. Now after applying the round n, it's generating a 128-bit cipher dice. So this is the general format of AES algorithm. So here we are input 2 things in the add round key. First 128-bit plain text, second is a key. Now each and every round we are use a different sub key. In each and every round we are generating a different sub key, K0 to K10. Now let's see what type of transformation operation will be carried out in each and every round. So now first we are considering our plain text. The plain text is a 128-bit size. Now we can input 2 things in add round key. The first is a plain text and second is a round key 0. Now after applying, now in add round key we are performing an XOR operation on a plain text and a round key 0. After applying the add round key is generating the sum output. Now this output may be given input to the sub bytes. In the sub bytes we are substituting the bytes using the S box. The S box is a predefined table. We will see this in the next slide. Next slide. Now the output of the sub byte is given input will be given input to the shift rows. Now in the shift rows, number of rows are shifted to left. Now output of this shift rows will be given input to the mix column. In the mix column we are performing the multiplication operation of 2 matrices. Now after applying this, the output of the mix column will be given input to the add round key. Now the add round key, we are input the two things. The first is the round key 1, and the output of a mix output which are generating from the mix column. Now after applying the XOR operation, it's generating a 128-bit ciphertext. So this process is called the round 1. I already discussed in a round 1 we are performing 4 types of transformation operation. The first, subbyte, shift rows, mix column, add round key. Now the output of the round 1 will be given input to the next round. Round 2, 3, 4, 5, 6, 7 up to 7, 9. Now the same thing will be repeat up to round 9. Now in the last round we cannot consider the mix column. Now you can see the subbyte. Then in the last round we are considering the subbyte, shift rows, and the add round key. After applying the last round, it's generating a 128-bit ciphertext. And again here we are inputting the round key 10. So this all about the round operation. It means what type of operation will be carried out in a round 1 to 9. Now here I already discussed this thing. Okay, one add round key is applied before the first round, right? And the third transformation missing in the last round. In the last round, you can see here. In the last round, the mix column transformation operation is not there. Now let's see the AES structure. Now here in an AES, the plain text, your plain text is divided into the 16 byte. Now the size of the plain text is a 128 bit. Now the size of the plain text is a 128 bit, and it divided into the 16 byte because each and every input is stored in a state. Now state, it means the state is a one matrix, and why we use this matrix? We can store the intermediate result of input and the output. That's why we need a state over here. Now the plain text is divided into the 16 bytes. Now the 16 byte is given input to the next matrix, and it represents as an input state. Now I already discussed each and every input is stored. Each and every input can store in a matrix state. Now the output of each and every round and initial transformation can store in a matrix and in a state matrix. Now I already discussed in this AES algorithm, it representing in a matrix form. Input is representing a matrix form and output is also representing in a matrix form. Now here you can see the 16 byte output, the 16 bit plain text is representing in a matrix form. Now after applying this, after generating this matrix, it will be given input to the initial transformation, and another input is come from the key expansion. This is key, and the key is also the 16 byte. The key is also the 16 byte because here your input matrix is also 16 byte. Then your key is also the 16 byte. Now we can input two things in initial matrix. The first input of plain text, second is a key matrix. Now we are performing a XOR operation on in this. Now we are performing the XOR operation in the initial transformation. After applying the XOR operation, it's generating a one next matrix. and the result of this initial transformation is stored in a in this state matrix. And again, the size of this state matrix is a 16 byte. Now, the output of this matrix, will be given input to the next round, round 1. Again, here we are performing a 4-type transformation, and we are passing the key also, and the key size also 16 byte. Now, after applying the round 1 operation, it's generating some output, and this output is stored in a state matrix. Now we will repeat this same. Now we will do the same process up to the round 9. Now after round 10, the output of the round 10 will be given input. Now the output of the round 10 is stored in the state matrix. After that, it's generating a 16 byte ciphertext or 128-bit ciphertext. So now you can see in this rectangle box, in this square box, the initialization, that means the expand the 16 byte key to get the actual key block to be used. Now I already discussed the 16 byte key to get actual key block to be used. Now we initialize the 16 byte plain text block called as state. Now you can see here, this is called the state. You can see this is called the state. Now XOR the state with the key block. I already discussed here. We have to perform the XOR operation with the key and the plain text. Now for each round we are performing a 4 transformation operation. In the first round we are performing a apply S box. Now rotate the row state. Now in the third step mix column, and the fourth step add round key. In add round key we are performing a XOR operation with the key. So this is the simple structure of AES. I hope you clear this idea. Now how to represent the number of block into the state. So let's see one diagram. Here you can see this figure. The B1, B0, B1, B2, B3. This is the first block. B4, B5, B6, B7. This is the second block. Now third block and the fourth block. Now here the SI mode 4 comma I divided by 4. It means that if you apply this formula, you will get the first block. It means if we consider the I equal to 0, it means the 0 mode 4, you will get the 0, and I 0 mode 0 divided 4, you will get the 0. So now you will get the block. Now you get the block 0 over here. If your I equal to 0. Now in the state, how to represent this state over here? Here you are given one row, number of block in a row. Now take the first block B0, B1, B2, B3 and represent in a state. Now this block is stored in a column like B0, B1, B2, B3. Now take the next block B4, B5, B6, B7 and representing in a state in a column. It's representing in a state like this B4, B5, B6, B7. It means take the block and it put into the column wise. So B4, B5, B6, B7. Like this you can fill this state. Now here this S of 0, 0, S of 0, 1, it means that the S0, 0, it means the zeroed state, zeroed word. S10, it means the first state, zeroed word. It means I already discussed. Okay, in a key, we input the 4 words. It means the key is defined as a words. It means that each and every key we are input the 4 words. So now here, if we are considering the S of 0 2, it means the 0 state and the 2 second word. Like this you can read this state. Now here the same thing, if I want to find the block of I plus 4j, it means that if your I equal to 0 and j equal to 0, it means that the block 0 plus 4 times 0, that means you will get the S of 0 0. Now the I equal to 1 and j equal to 1, it means that the block 1 plus 4 times 1, you will get the 4. So 4, it means the I equal to 1 and j equal to 4. So now you will get the S1 4. So this is the simple representation of this block. So I hope you clear this idea. Now the plain text to state, it means now we are considering the plain text message and how to represent this plain text into the state matrix. So now here you can see you have given this text, AES, right? AES USER, this is you have given this text. Now first of all you have to convert this text into the hexadecimal number. So now if you are considering the A, its hexadecimal number is 00. Now we are considering the E, its hexadecimal number is 04. Now we will take the first block 00, 04, 12 and 14. Now it representing in a column. Now it is stored. Now we can put in a column wise. Now take the first block and put into the state by column wise. So now 0, 0, 04, 12, 14. Now 0, 0, 04, 12 and 14. Now take the second block 12, 04, 12, 00. Now it represented in the matrix form. It represented in a column. It's stored in a column wise. 12, 04, 12, 00. Like this, you have to create your first state like this. So I hope you clear this idea. Now, thank you.